All right, here we go. First video for you all. I practiced with some other classes. I feel like I've gotten okay with it. Not happy about my voice. I think it sounds funny. So it is what it is. Here we go. Section 5.1. Start. So in Chapter 5, what we're going to be doing is the same stuff we were doing before with solving these differential equations, but now we're just not going to look at one differential equation, we're going to look at a system of differential equations. Section 1 is all about solving this one problem. So here we go. Just to read through it, two large tanks, each holding 24 liters of a brine solution, are interconnected by pipes shown in the figure below. Fresh water flows into tank A at a rate of 6 liters per minute, and fluid is drained out of tank B at the same rate. Also, 8 liters per minute of fluid are pumped from tank A to B, and 2 liters per minute from tank B to tank A. The liquids inside each tank are kept well stirred so that each mixture is homogeneous. If initially the brine solution in tank A contains X of 0 kilograms of salt, and that in tank B initially contains Y sub 0 kilograms of salt, determine the mass of salt in each tank at time t is greater than 0. Okay, before we look at the picture down there, I do want to say that something like this actually just came up for me recently. And I know it's lame, but I was playing this video game. So this video game is all about, like moving products around. You own this quarry. It doesn't matter. In the video game, you're trying to generate power. And the way to generate power is you build a steam engine. So with the steam engine, you input steam into the engine, and it also outputs steam. Because that's all that happens, right? You just run steam through it. It starts off as pressurized steam, and it just kind of changes into non-pressurized steam in the end. But what you can do is you can hook up multiple of these steam engines together and just have the steam from one output into the steam of another. And then the output of the second steam engine, you would repressurize and plug it back into the first to generate kind of the cycle. But of course you're losing pressurization and you're losing steam over time, so you have to input steam into the system and you'd be outputting just plain water at the end. The point of all that is that something like this, as crazy as it is, actually came up for me not too long ago. All right, let's jump into this question, though, where we're talking about salt. So we have tank A and we have tank B. We are inputting 6 liters per minute of just pure water into tank A. We're going to let X sub T represent just the amount of salt in this tank at time T. This tank holds 24 liters, and it is not losing liters per minute overall. We have 6 coming in, 8 going out, 2 going in. So overall, we have 8 coming in and 8 going out, so this is just going to stay at 24. We also have this initial amount of salt at time 0, so we're just going to let that be X of 0. In tank B, we have a similar situation. Y is going to represent the amount of salt at times T. This also holds 24 liters. It starts off with an initial amount. We have 8 coming in. So we have 2 going out back to A, and we have 6 going out of the system in total. Overall, this is also not losing any liters of solution. All right. To set this up, we're going to start with the same thing that we always do with these containment systems. We're going to look at the differential equation where the change in salt, I don't know why I'm typing it out here, it's on that same page. The change is just the input rate minus the output rate. So dx dt is going to be the amount of salt that's coming in minus the salt going out. dy dt would be for tank B, the salt going in minus the salt going out. So I'm not going to bother writing that. Let's split this up into our 2 separate tanks. So we're going to have tank A, and tank A is going to have the change, dx dt. This we're just going to let be the input rate minus the output rate. So let's go back to our picture here and let's talk about the input rate for tank A. There is no salt coming into the system from this 6. because remember this is pure water. The only salt that could be coming into tank A would be salt coming from tank B with this 2 liters per minute. So it's going to be the 2 liters per minute coming in at the concentration of B. So the 2 liters per minute coming in, and then the concentration of salt in B is going to be the amount of salt divided by the 24 liters that's always in tank B. So this is the salt coming in to tank A. We're going to subtract that by the salt going out of tank A. The only salt going out of tank A is going through this pipe at the 8 liters per minute into B. So it's going to be the 8 liters per minute going out times the concentration. The concentration in tank A is going to be X divided by 24. All right, let's jump to B. So with B, this is also going to be a derivative, but this is going to be dy dt, the amount of change in salt, y, with respect to time. It's going to be the input rate, the amount of salt going in. For B, the only salt that's coming in is coming from A through this pipe, the 8 liters per minute. So it's going to be the 8 times the concentration, which is going to be the X over 24. And that's going to be minus the salt going out. So the salt going out of B is going to actually have 2 different parts to it, right? It's going to have the 2 that's going into A, and it's going to have the 6 that's going out of the system. Because the concentration in B is the same everywhere, I'm just going to combine this together and say overall I have 8 going out with the concentration of B. So minus 8, and the concentration of B, remember, was y over 24. So I can clean both of these up a little bit just by multiplying and rewriting that as a fraction. So that first thing's going to be 1/12 times y minus 1/3 times x. For this one here, simplifying those fractions down, 1/3 x minus 1/3 y. All right, I'm going to just to clean up my system a little bit and rewriting it. Instead of dx dt, I'll just leave it as x prime. So we're going to have x prime is that negative 1/3 x plus 1/12 y. And then y prime, I'll just leave that one as is, 1/3 x minus 1/3 y. So all I'm doing here is I'm putting the x over the x and the y over the y. This 2 equations is what we're going to call our system. So this is my system of differential equations. I know that this looks daunting to solve, but it really isn't too bad. It's just going to take us some time. We're going to solve this using substitution, just like you would if they were not differential equations. So what we're going to do is we're going to solve for x here in my second equation. It doesn't matter which variable you solve for, just pick one that's easy to solve for and solve for it. So if I solve for x here in the second equation, I'll let you do it. It isn't too hard. X is going to be 3y prime plus y. All right, then remember we're going to be substituting this into equation 1. All right, so if I substitute x equals 3y prime plus y into the, x is not supposed to be in the denominator. Didn't even see that. All right, so we're going to plug this x here and plug it in for this x up top here, and we'll get this. X prime is going to be that negative 1/3 times. Now my x is 3y prime plus y, and then that's still going to be plus the 1/12 y on the end. And then cleaning this up a little bit, again, not hard to clean up. You just got to be a little bit careful with it. Oh, sorry, I forgot something. Not only should I have substituted the x in for this x like we did, I should also have substituted the derivative of this in for the x prime. So I forgot to do that. Let's fix that now. So instead of an x prime out in front here, this is going to be the derivative of this. But to take the derivative of this, you just got to be a little bit careful. It's not too bad with this one, but if it was more complicated, you have to do some impartial stuff. This one's just going to be 3y double prime plus y prime. Okay, and then cleaning this up a little bit, this is now going to be a second order linear differential equation, the stuff we were doing back in section 4. If you were to factor it all out and combine like terms together, we have the 3y double prime plus 2y prime plus 1/4 y, and that's all going to be equal to 0. This we spent weeks, months solving these kinds of things. I know you can do it. Remember, to solve these, we would find the auxiliary equation. I'm just going to put dot, dot, dot here. If you did do the auxiliary equation, you'd get two different R values, -1/2 and -1/6. That means that the solution to this homogeneous equation would be in the form C sub 1 e to that -1/2 t plus the C2 e to the other one, -1/6 t. Okay, cool. Now, this is the y. Like, we have now solved for y. We just have to go back and solve for x. And it's not too hard because we know what x is in terms of y. X is just 3y prime plus y, so we're just going to do that. So we're going to substitute this into x equals the 3y prime plus y. So substituting that into there, we get x is 3 times c sub 1. Oh, you know what I can do? Because this is super fancy. No, I'm not going to do it. I'll write it all out. So x is going to be 3 times this thing's derivative. So we're going to bring down the -1/2. Still have that C1, and we're going to leave that e to the -1/2 t. Taking the derivative of this term, bringing down the -1/6 C2, and we still have that e to the -1/6 t. Alright, so it's going to be that thing, and then plus just y itself, which is the C1 e to the -1/2 t, plus the C2 e to the -1/6 t. And you combine like terms together, so I'm just going to dot, dot, dot this one as well. You end up with -1/2 c sub 1 e to the -1/2 t plus 1/2 c sub 2 e to the -1/6 t. And that's pretty much it. So we've now found y. Y is this. X is this. The only other thing that you'd have to do is we would need to use the initial conditions to find the c sub 1 and the c sub 2. It does not matter which one you do, of course, because they're the same C1 and C2 in both of these. So just kind of play around with it and fiddle with it. Unfortunately, it's not going to look anything too nice for this question, because remember we didn't even have numbers for the initial conditions. We just had x sub 0 as x naught and y sub 0 as y naught. So here you would just plug y naught in for the y, and then plug 0 into the t's. You plug x naught in for the x, and then 0 in for the t's, and then you have a system with the C1 and the C2. So not so bad. So just to finish this one up, I'll say that remember that x at 0 we set to be x naught, just a generic constant, and y of 0 we set to be y naught, just a generic constant. But plug those into these two solutions, and that's it to find the C1 and C2. So I know this question looks very, very complicated, and it is, but writing it all out, it's not too bad. You come up with your system of equations, choose a variable and solve for it, substitute that into the other equation, you're going to end up with something a little bit complicated. Here we have a homogeneous second-order differential equation, but from Chapter 4 we learned how to solve these, and we solve for y. Once you have y, just plug that back in, and you get x. This is going to be my two solutions, x and y, to my differential equation system up top. Last thing you'd have to do is to figure out your x naught and y naught, figure out your C1 and C2 based on the initial conditions.